It's time to talk about Decorator Pattern. If you're new to this playlist, I just want to quickly tell you that what we're doing is that we're walking through all of the patterns in this book, head first, design patterns, one by one by one. So in total there will be something like 12 to 13 to 14 videos because we'll split some of them into multiple videos. So if you're not already subscribed to the channel, be sure to subscribe to the channel so that you won't miss the next pattern. But now, the Decorator Pattern. So before we go any further, I just want to warn you that the example that's found in the head first book is, in my opinion, not really suitable for a decorator pattern. In other words, it's a good example for illustrating how decorator pattern works and how you sort of syntactically string the pieces together. But I don't think, and people are free to disagree, but I don't think that it should be taken literally. I don't think that the example that they report is actually a sensible use case for using decorator pattern. We'll return to that, but I just want you to remember that as we go through the example. And in the end, I'll give you some examples of what I find to be more suitable use cases for decorator pattern and when I've actually used it in real-world scenarios while coding myself. But now, what is actually decorator pattern? Let's start on a high level. I think it could be explained in multiple ways, but here are two. So the first one is, decorator pattern essentially is about you having an object, and instead of simply sending messages to this object, this could be speak, you send the message speak, and you expect the object to return, for example, a string back. So you send the message speak, and the object returns, it responds with the string hello world. Now, decorator pattern is a way of saying that if I want to change the thing that's returned, if I want to change the behavior of this method, I could actually do that at runtime without changing the contents of this particular object. So you change it at runtime and not at compile time. And when we say change at runtime and not change at compile time, you can simply think of that as changing the behavior of this thing without actually rewriting the contents of this thing, without actually opening up the class and changing the contents of that file. So with decorator pattern, what we do is instead that we say, let's actually wrap this object in another object. I'll remove these arrows. And when I send the message speak, I'll send the message to the outer object, who will send the message to the inner object, who will send the message out back to the outer object, who will return it back to me. And then we can keep on doing this indefinitely. And this is the essence of the decorator pattern. You can take another object, you wrap this wrapped object, you wrap the wrapper in another wrapper. So another object that sends the message to the inner wrapper, that sends the message to the inner object, that then returns to the inner wrapper, that returns to the outer wrapper, and then returns back to you. So it seems kind of convoluted, but you'll see why this is actually very valuable. So you have an object that wraps another object, that wraps another object. And the point here, let's move to the second explanation, is that, so you have the object in the middle, and we'll refer to this as the component, but this one, the one wrapping the component is a decorator, and the one wrapping the decorator is a decorator. If you just think about a single one of these decorators, the decorator has a component and is a component. We're going to get back to this, but essentially, remember that from the beginning we said that I take this original object and I want to send the message speak, and then I'll get something back. And now that we've wrapped it in two decorators, these two decorators actually behave from the outside, from the interface standpoint. They are, as in ISA, they are of the same type as this thing. In other words, they are exchangeable. So whenever you have this thing, you could use this thing instead, or you could use this thing. You wrap the original object and then you can use the wrapper and pass that around as if it was one of these original things. So the first time I heard the sentence, it is a and has a of the same type, it kind of blew my mind. I'm like, what is this crazy pattern? And actually it's kind of cool. It's very similar to composite pattern that we'll talk about later, but composite is significantly more complicated. But you can think of it this way. The decorator is of the same type as this because you want to be able to treat it as if it was one of these things. That's similar to proxy pattern that we'll talk about later. And the has a portion, the fact that it has one of these types, is because you want to be able to send the message downwards and then back up. That's why it has a. But enough with the abstract nonsense, let's get into something more concrete. So let's look at the definition from the head first book. By the way, if you're new to design patterns, I highly recommend you to get this book. The link is in the description. It's an affiliate link, so if you use that link, I'll get a kickback, and if you do, thank you, that helps massively. But now, moving on. So here's what they say. The decorator pattern attaches additional responsibilities to an object dynamically. Decorators provide a flexible alternative to subclassing for extending functionality. Let's break this down. The decorator pattern attaches additional responsibilities to an object. Okay, so that means this object was originally doing something, but now using decorator pattern, we attach additional responsibilities. This outer circle attaches some set of responsibilities, and this even outer circle attaches some other responsibilities. And remember, attaches additional responsibilities to an object dynamically. And that's what we're talking about at runtime or at compile time. You can attach different responsibilities at runtime. You don't have to set your mind to a particular set of responsibilities at compile time. That's what they mean when they say dynamically. Next sentence. Decorators provide a flexible alternative to subclassing. We'll actually specifically look at this because the example that they have of a situation where you might feel that you possibly need something like decorator pattern is a class explosion scenario where you have too many subclasses. So you can think of it this way. Think about that classical saying, inheritance is not for code reuse. Inheritance is not for sharing behavior. So it's a way of using composition rather than inheritance in order to share behavior. Remember what we said before, we will use inheritance, we will use ISA, but only to make this thing behave as if it was one of these things, right? We're not using inheritance to share behavior. We're using composition to share behavior. We'll get into this. But we're going to use inheritance to make sure that this thing behaves as if it was this inner thing. You can also think of it this way. If you define subclass A, subclass B, subclass C, then you only have A, B, C. You can't somehow compose a new class at runtime that's a composition of A and B or B and C. But with decorators, that's actually what we're doing. We're defining the decorator A, the decorator B, and the decorator C. And then you can actually compose, you can use both decorator A and decorator B at the same time. So it's more flexible, but we'll get into this. So decorators provide a flexible alternative to subclassing for extending functionality. And that's what we were talking about. So that's the definition. In the book, they use an example of a coffee house called Starbucks Coffee. So essentially, it's about constructing a menu of products that can be ordered at the coffee house. So it's a bunch of different coffee types, I guess. So a customer comes in and asks for a particular type of coffee, and they have tons and tons of variations of coffee. So here's what they start with. Remember that now we're talking about a bad example. So this is not a suggestion of what you should do. This is an illustration of something that's problematic. So they have a class called beverage that has two methods. Get description. I'll just write get desk in order to save myself the space, but again, remember to always use proper method names and variable names, but just to save space. So get desk for get description, and it has another method called cost. And this beverage class is an abstract class. If you're not familiar with abstract classes are essentially classes that cannot be instantiated. So something has to inherit from beverage, and then you can instantiate this thing, but you can never instantiate this thing. The reason for using an abstract class instead of an interface is that an interface cannot have an implementation, right? You cannot put implementation details in, for example, the cost method. But if you have an abstract class, you can actually put a default implementation here in the cost method, but you can't instantiate the beverage. But however, if you have coffee, for example, then you could instantiate a coffee, and if cost has an implementation here in the abstract class, then coffee will get that implementation for the cost method. That wouldn't be possible if you have an interface, because then you would define the existence of a method called cost, but you would have to define an implementation in the coffee class. Coffee class is responsible for implementing cost, and it can't inherit it from something. So an abstract class is a way of defining a class that defines some baseline implementation or some default behavior that other classes can inherit, but the abstract class is not instantiatable. You can't instantiate an instance of the abstract class. Moving on. So that's the abstract class. And then they have a few basic types of coffee. So they have, for example, decaf, and they have espresso. And then they have a few more types, but I mean, in order to save space, let's just not consider them. But the other types that they have are house blend and dark roast. But I mean, you get the point. You can have multiple types of coffee that inherits from the beverage abstract class. And the method that they define is cost, because the baseline cost of an espresso is different from the baseline cost of a decaf coffee, given the scenario that we're looking at right now, right? So when I talked about the abstract class before, sharing behavior, I think I used the cost method as an example, but what actually happens here is that get description, that method has a default implementation that is not overridden here, or is not implemented here in espresso nor in decaf. which means that the getDescription method is defined in this class, and thus these subclasses will use this implementation. However, cost is probably not defined here, or you could have a default implementation here, but regardless, it's possible to override here in decaf and here in espresso. So decaf has some cost and espresso has some other cost, which could potentially be the same or potentially not, but given the example, probably not the same. So the point here is that they have these sort of base kinds of coffee, but then the crux is that they have a bunch of extras that you can get with your coffee or in your coffee, which they in the book later call condiments, but you can think of them as extras or as flavors or as toppings or as spicings. So to be more specific, these are things such as steamed milk, whipped milk, mocha, soy milk, etc, etc, etc. And this is also the first point where I feel that their example is, apologies, but kind of stupid, because who would ever then think that it's a reasonable idea to start to introduce a single class for each combination of these different things? Because the problem that they're pointing towards is, of course, that you could have both a mocha coffee with steamed milk, but you could also have a mocha coffee with whipped milk, or you could have a mocha coffee with soy milk. Or if you think about the flavor caramel, then you could have a soy milk with caramel, or whipped milk and caramel, etc, etc, etc. Just think about, like, if you define a few of these different flavors, and then just imagine that any flavor could be combined with any other flavor, because why not? I mean, people could come up with the strangest orders, which makes sense if you're a coffee house, right? You want to actually serve the people who want you to mix different things. Just think about if you've ever been to Starbucks or Espresso House or any of these places. I mean, of course you can get crazy combinations of the toppings or the extras that they have. And if you introduce a single class for each combination, right? You have steamed milk caramel, whipped milk caramel, etc, etc, etc. If the first one is a class, the second one is a class, the third one is a class, each and all of these are different classes, then you'll have what is commonly referred to as a class explosion. You'll very quickly find yourself in a scenario where you have tons and tons of classes, and they all do very, very small things, right? So from single responsibility principle's point of view, maybe that's a good thing because they do only a very small thing, but it's completely unmanageable because you have so many of them. And instead of me actually drawing this here, let me just show you this picture, and I think you'll understand what I'm saying. So a serious class explosion. So that's an example of a poor way of approaching this problem. So then they suggest another poor way of approaching this problem that might also actually be intuitive to a lot of people, especially when you're new to programming. So the second suggestion that they have is to say that all of these different things, like whipped milk, soy milk, caramel, etc., could be treated as booleans, could be treated as true or false values. So the concept of having steamed milk could be treated as a boolean, where if you put steamed milk into the coffee, has steamed milk is true. If you don't, then it's false. That's kind of simple, right? So you just enumerate all of the different things, so which means that we need some more space here. So we add decaf and espresso, both having the cost method and both inheriting from beverage. And then in beverage, we put all of these booleans. So has milk, has soy, has caramel, has whipped, and so forth and so forth and so forth. And actually whipped was probably whipped cream rather than whipped milk, but whatever. And actually, because of the examples in the book are in Java, they're not using getters and setters that you have in C#. So these would correspond to getters, but they also in the book define setters. So you don't only have has milk, you also have set milk. So you say set milk, which sets milk to true, or you say set milk and pass a boolean, so setting it to true or false. But I mean, that's irrelevant to this example. Of course, you could also pass these through the constructor, for example, right? So you could have, upon creation of a beverage, you supply 1, 2, 3, 4 booleans. So true for milk, false for soy, etc, etc, etc. And I mean, you can see that for one, this is extremely unexpressive to pass all of those in. And even setting these as parameters feels very odd. I think Sandy Metz has a great saying when she says that conditionals breed. So if you have one conditional, that will likely put you in a place where eventually you'll put even more conditionals in your program. And I can't remember who said this, please put that in the comments if you remember, but somebody said that returning booleans usually provokes conditionals elsewhere in your system. So the fact that we're returning a boolean will provoke the need to, at some other place, switch over that conditional. In other words, include that conditional in some kind of switch statement or if statement or something like this, essentially in some kind of condition. And the idea that you should stay away from conditionals is a topic for another discussion. Let me know when we can have that discussion. But beyond these problems, there are some other problems that they highlight in the Head First book. One of them is that you have to change existing source code when you want to add a new condiment or when you want to add a new extra, a new flavor. So if you want to introduce chocolate, for example, so maybe you want to put chocolate in your coffee, then you have to actually change the contents of this class by introducing has chocolate, ? And this violates the open-closed principle, so that's why they're suggesting that's a bad idea. But I think perhaps even a more severe problem that they're also highlighting is the fact that because these are inheriting from beverage, they'll also inherit all of the methods here. So perhaps you're already familiar with the interface segregation principle and Liskov substitution principle. These are two of the principles from the solid design principles of object-oriented programming. And the interface segregation principle states that a subclass should not be forced to depend on methods that it does not use. So for example, they actually have a very great example in this book. The example is that what if you introduce tea and make tea inherit from beverage? Because it is a beverage and you want to be able to treat all of the beverages, all of the menu items the same, so you can print them to the menu. But what if some of the methods that we've put here actually don't apply to tea? So hypothetically, I mean, maybe these do, I apologize if these do, but maybe chocolate simply doesn't apply to tea. Like, it's so absurd that you can't order it. You can't order tea with has chocolate. Then we're explicitly breaking the interface segregation principle because we're forcing, because tea is inheriting from beverage, and we're forcing tea to actually have the default implementation, the implementation in the abstract class of has chocolate, even though it doesn't want to use it. So if you're interested in the interface segregation principle, I've talked about that previously in another video, so if you're interested, I'll link that in the show notes. Check it out. But shortly, the problem is that if you just think of an example where you have an instance of the T class, you could have an instance of a T class without knowing that it's a T class because you're treating it as a beverage, right? That's the point of having inheritance. So you have an instance of a T class, you have an object that's of type T, but you're treating it as a beverage. And because you only know that it's a beverage, you could call has chocolate. But T surely doesn't have chocolate. And now in this particular scenario, that's not necessarily too dangerous. But on the general plane, that's a crazy idea. Because this method simply doesn't apply to this class. It's not that it's not doing anything, it's just that it's completely undefined. It just doesn't make any sense within the context of T. And that's why we should separate these. So the interface segregation principle essentially says that it's better to have multiple smaller interfaces than one single large one, which is exactly what we have here, a single large interface. Another problem with this design that they raise in this book is that they say, what if a customer wants, now I didn't put mocha here, but their example is, what if the customer wants a double mocha? A better example perhaps might be an espresso shot. I mean, most coffee houses have it so that you can get your coffee and then you can get a shot of espresso in your coffee, in whatever coffee you had. And then if you just think about the concept of one shot of espresso, if you can have one, of course you could have two. And if you could have two, then why not have three, hypothetically, right? And that means that you would have has espresso shot, but then you would also need to have has double espresso shot, and then has triple espresso shot. And then you're also in a sticky situation where you have to say, okay, if I have a triple espresso shot, I shouldn't also set has double espresso shot to true. So that's kind of tricky to manage, but also kind of stupid, because the second espresso shot is just another one of the same thing. So why would that have to be a second one? But of course, then you could also think about strange designs, such as saying that, okay, instead of making that a boolean, you would make that an integer, and then you count the number of times that you have. But I mean, hopefully you're feeling that we're sort of treading down a slippery path where it's just going to get more complicated. And then you would have to calculate the cost. I mean, so obviously, maybe I didn't mention that before, but the point of keeping track of all these things is that the cost varies based on what kind of condiments you're actually putting into your coffee. So then the calculation of the cost method, how to actually calculate the cost of this particular beverage, becomes very complicated when you think about has espresso shot being an integer and has soy being a boolean. So you'd have to have some nasty logic for the cost method where you would say, okay, if it has 4 espresso shots, then it's this price. If it's 2 of espresso shot, then it's this price. But then plus the fact that you have soy, which makes it this. So if has soy, la la la, etc., etc., etc. I mean, hairy, very hairy. So not a good idea. Right? What can we do? And this is when the decorator pattern comes in. So let's start off by looking at the decorator pattern applied to this particular example, and then after that we'll look at sort of the generalized UML diagram and talk about the decorator pattern in general. And again, remember that I'm not saying that decorator pattern is actually suitable for this example that they've chosen. This illustrates the way you use decorator pattern very well, but I don't actually think that this particular use case is suitable for decorator pattern. Moving on, let's check it out. So we start off with the class beverage again. The beverage has get description, and it has price, and it has cost. So cost returns to the price of this particular beverage, and get description returns some kind of string representation of the contents of this particular beverage. Again, remember that it could get complicated because you can have all of these different condiments, all of these different extras, all of these different add-ons. And then we have those two basic types that we had before. We have decaf and we have espresso. And both of these have their own implementation of the cost method because, again, they have different baseline costs. So the price of an espresso is different from the price of a decaf, assuming you put either no other condiments or you put the same condiments in them. Now, how do we make use of decorator pattern? Instead of introducing multiple classes that represent all of the different combinations of the condiments. You have espresso with mocha, espresso with caramel, and so forth and so forth. Instead of that, what we'll do is that we'll introduce a condiment decorator. But because of the length of the word condiment, I'll just use the word add-on instead. I'm meaning the same thing, it's just to make this simple. So it's an add-on to your sort of baseline coffee. So you have the baseline coffee and then you add on something else, such as whipped cream. So we'll call this add-on. So add-on decorator, which implements the method get description. But remember what we said in the beginning about decorator pattern. The essence of the decorator pattern is that the decorator is a component and has a component. So this arrow denotes that it is a beverage, but it also has a beverage. So the add-on decorator is a beverage. It behaves as if it were a beverage. So you can call get description, just like you can call get description here. Sorry, I should use the same name because we mean the same method. I use the short notation get desk. You can call get desk on an add-on decorator because it is a beverage, and you can call cost, even though we don't define cost here, because all beverages have costs, and if the cost has a baseline implementation here, then you have an implementation for cost, and you can call cost in the add-on decorator. So then it behaves as if it were a beverage, because it is a beverage, but it also has a beverage. We'll get into more about why this is and what this means. But what we then do is that we say that the add-on decorator has a number of implementations. A number of different classes are add-on decorators. So I'll just do two, but you have to realize that you can have as many as you want, and that's the point. That, right? We were talking about different condiments before, different add-ons, like soy and whipped cream and caramel and chocolate and so forth and so forth and so forth. And all of these could be different add-on decorators, or in the book, condiment decorators. So let's do one. Let's say caramel. So caramel. Now, if I would put this in code, I would probably actually call this caramel decorator, just to make it very clear to the person that this is a decorator. Remember the power of using semantic naming, of using proper naming so that other people can understand what you're actually doing. But here, to save space, and as they've done in the book, I'll just call this caramel. And let's choose another one with soy. And these that are decorators, that are add-on decorators, these implement both get description and cost. So both of them have get desk and they have cost. And this might seem really odd, and don't be frightened, but it's actually kind of smart. So the point here is that, remember the original image that we drew, where we had one class in the middle and then something that wrapped it and another thing that wrapped it. Here's the point. The object in the middle, right, the instantiated object in the middle, that's a beverage. The thing here, the thing that wraps it, the first decorator, is an add-on decorator. It's an add-on decorator that is a beverage. It behaves as if it were a beverage, but it also has a beverage. And that's what we're trying to denote when we're drawing it outside, or like as if it were containing this inner object, this beverage. So this thing is an add-on decorator. And this thing is actually an add-on decorator as well. So we have an add-on decorator, as in the type. We have an add-on decorator that wraps another add-on decorator that wraps the beverage. And concretely, now we're talking about what sort of abstractions they are of, but if we talk concretely, this object has to be either, given that these are the only classes that we have, it has to be either an espresso instance, an instance of the espresso class, or it has to be an instance of the decaf class, because this is a beverage. And this decorator and this decorator has to be either a caramel decorator, or it has to be a soy decorator. One of them. So this could be caramel and caramel, or caramel and soy, etc., etc. All of the different combinations that you can imagine. So the point then is that with this design, what we've constructed is that we've constructed a situation where instead of having a single class that describes decaf, a single class that describes espresso, a single class that describes decaf with caramel, a single class that describes espresso with caramel, a single class that describes decaf with caramel and soy, a single class that describes espresso with caramel and soy, and so forth and so forth. Instead of having all of those classes in the class explosion scenario, instead of that, what we've done is that we've separated the concerns like this, and we decorate in all of the different add-ons that we want to add to the coffee. So how do we do that? We wrap them. So with this design, you can create an espresso with caramel. You could create just an espresso. You could create an espresso with caramel and soy by saying, I'll create an instance of espresso, then I'll pass that instance of espresso to a caramel, and then I'll pass that instance of a caramel decorated espresso to an instance of a soy class. Essentially making that a soy decorated, caramel decorated espresso, right? And you can see the critique creeping up of the fact that this design pattern often makes it much more difficult to reason about your code. And after you've wrapped it and wrapped it and wrapped it and wrapped it, it's kind of tricky to remember what you actually have. And as far as I understand, if you're interested in order, if you're interested in the order of how you wrap things, and this design pattern is not suitable for that scenario. But that's a different discussion. So we haven't really talked about what get description and what cost, what these two methods do. So let's quickly talk about that. Let's actually only talk about the cost method, because I think you can figure out how get description works in exactly the same way. So the point is, again, that depending on which add-ons you put into your coffee, the price will be different. So remember that the idea of the cost method is that it returns a number that represents the cost. So for the sake of simplicity, let's just say that it returns an int. So the cost methods here in the beverage classes, these cost methods, they in some sense return the baseline cost. So if you just order an espresso, then this is what you'll get. So say the price of an espresso is 1 and the price of a decaf is 2. Hypothetically, I mean, never mind the currency and never mind the relative pricing. Let's just say that these are the prices. And then let's say that when you add caramel to whichever beverage you already have, you add an additional 2 to whatever cost you already have. And let's say that when you add soy, you add an additional 1 to whatever cost you have. So if you get, hypothetically, if you get an espresso with caramel and soy, then you should have 1 plus 2 plus 1. So 3 plus 1, 4. So the price of an espresso with caramel and soy should be 1 plus 2 plus 1. So 1, 3, 4. And in the same way for all of the different combinations. So if you get a decaf that has a baseline cost of 2, and then you only add caramel, then you add 2, and then you also end up with a price 4, and so forth and so forth. I think you can see how that works. But how do we actually implement that? What is the implementation of this method? And why isn't it actually the same as this method? Because if you think about it, you could just keep wrapping decorators and decorators and decorators. Why do you need to have something here that's different from the decorators? If you're familiar with recursion, you can think of it as that this is the base case. So you're using recursion to go down the chain of decorators, but then at some point you need to reach the base case, which is this cost, and then you can go back up. But if you're not familiar with recursion, never mind, we'll have that discussion some other time. You can just think of it this way. This cost is an add-on. This is not the baseline cost. This is a cost that can only exist if you have another cost that it adds to. This cost is existent in and of itself. This is the baseline cost. You can get this thing in and of itself. You cannot get a decorator in and of itself. Caramel just by itself doesn't make any sense, right? Imagine you go to the counter and you say, can I just have some caramel? And then you stick out your hands, or you just, I don't know, drink it from the machine or whatever. Essentially, that doesn't make any sense within the scenario. So decorators have to wrap something that can exist in and of itself. So if you think about the implementation of cost here, when we say that the cost here returns 1, we actually mean that explicitly the implementation of this method would probably be something like return 1, semicolon, done. That would be the implementation of the cost method. And same thing here, return 2. Implementation of that method. But the cost method here, what that does is that it would say something like, remember that the cost of it is 2. So it would say something like return this dot beverage dot cost plus 2. So this dot beverage, we haven't talked about this, but this dot beverage refers to the fact that it has a beverage. This thing wraps another thing. And when this thing says this dot beverage, it refers to this thing. When this thing says this dot beverage, it refers to this thing. When this outer thing says this.beverage, it refers to this thing. So from the outside, it refers inwards. So it refers to the thing it's wrapping. The decorator refers to the thing it's wrapping. And in this case, the thing it's wrapping happens to be another decorator. But this thing, when it refers to its beverage, it happens to be an actual beverage. So that's why we're saying, get the cost of the thing I'm wrapping, because my cost is supposed to be added to that cost, right? We're saying plus here. It's supposed to be added to this cost. We take the baseline cost, which is the baseline cost if we're here, right? If we're here, this.beverage refers to this, which is the baseline cost. But if we're here, it refers to this cost plus this cost. So essentially this stuff, right? And if we're here on the outside and we say this.beverage.cost, we're referring to the cost of this stuff, of the total price of the thing that you are wrapping. Because if you think about it, this thing, this outermost thing, only knows that it's wrapping something. And it's agnostic to what it's wrapping as long as it's of type beverage. It wraps something that's of type beverage, and it has no idea whether the thing that it's wrapping actually also is a decorator that wraps a thing, that wraps a thing, that wraps a thing, etc., etc., etc. And then at some point down the chain, you end up with a beverage. It has no idea. It just knows that it wraps something that calls itself of type beverage. And then it says, okay, give me the cost for your thing. So it's like a black box, right? Every decorator thinks that it's only wrapping a single thing, but that single thing might also be a decorator that thinks that it's wrapping a single thing. And that thing might be a decorator that thinks that it's wrapping a single thing. And so forth and so forth and so forth. So when you want to compute, when you ask this thing, hey, what's the cost? It says, actually, for me to be able to report the cost, I need to figure out what the cost is of the thing I'm wrapping and then add to that the cost that I have for myself. If this thing is caramel, then this thing should add 2. So it should say, what's the cost of this thing that I'm wrapping? And then let me add 2 to that, because that's the cost of the caramel add-on. And this is why it says, this.beverage, let me return the price of the thing that I have. I am a decorator. I have a beverage, which might be a decorator or it might be a baseline beverage. Let me ask for the cost of that thing, and then let me add whatever I want to that. And get description behaves in exactly the same way, essentially. The difference is, of course, that works with strings, and this example, it's a way of composing together a name that represents the whole beverage. For example, could say espresso, caramel, soy, or something like this, right? It's in some sense a way of iterating through this data structure. It's a way of traversing this data structure, which is, by the way, if you're familiar with that, very similar to a linked list. It's a node that points to a node that points to a node, etc. And returning and aggregating some kind of result. So in the get description example, we aggregate a string. In the cost example, we aggregate a number. Now, let's look at the generalized UML diagram. So the generalized UML diagram looks something like this. You have a component. In our previous case, it was a beverage. You have some set of methods on this. So we'll say method A, method B. You can't define them here in the general case because it entirely depends on what you're actually building. You have some methods, so let's call them A and B. Inheriting from the component is a concrete component, which has method A and method B. Inheriting because it is a component. In our previous case, we had an abstract class with a concrete class, but it could of course be an interface and a class. Then also inheriting from this component is a decorator. And the decorator, of course, also needs to specify method A and method B. But again, if it's an abstract class, perhaps it only overrides or defines some of the methods because some of them it may want to use from the component. Depends on your scenario. But because it's decorator pattern that we're looking at, the decorator not only is a component, it also has a component. So the decorator is a component, but it also has another component. So when you instantiate the decorator, you provide it a component. So the decorator behaves as a component, but also has a reference to another concrete component. And that component could be another decorator because a decorator is a component. And that's on the abstract level. So concretely, we of course need to have concrete decorators. So we have hypothetically concrete decorator A and concrete decorator B. Let me actually rename these from A and B to 1 and 2, just to emphasize that this A and B has nothing to do with the A and B's in the method names. So these also have method A and method B. B. Method A and method B. And concrete decorator 2 is a decorator. And that's it. That's the decorator pattern. You instantiate a component, you create an instance of a component. It behaves as a component, but it is a concrete component. Because this is an abstract class, you can't instantiate the abstract class. Or if this is an interface, you can't instantiate the interface. So you instantiate a concrete component, that's the concrete component. And then you wrap that, you give that to some kind of decorator. And of course, again, you can't instantiate an abstract decorator if this is an abstract class or if this is an interface. So you have to instantiate either this concrete decorator or this other concrete decorator. And then when you instantiate that concrete decorator, you pass it the component. And that's how you're wrapping that concrete component. So you're wrapping this concrete component within this concrete decorator. So when you instantiate the concrete decorator, you pass it the concrete component. And then perhaps you instantiate another decorator, perhaps the concrete decorator 2. So you instantiate the concrete decorator 2, and when you do that, you pass it the instance of the concrete decorator 1, which was wrapping the concrete component. And of course, you wouldn't have to do that because that's the power of the decorator pattern. You could instantiate the concrete decorator 2 and pass it the concrete component. So you would have something like that. So maybe this is the concrete component and this is decorator 1 and this is decorator 2 and this is the concrete component and this is decorator 2. That's the flexibility of decorator pattern. You can at runtime compose these in any way you want. So before we look at some code in order to wrap this up, let's just quickly go back to the definition from this book. So the book said that the decorator pattern attaches additional responsibilities to an object dynamically. So these are the additional responsibilities. We're saying this defines some kind of additional responsibility and this defines some other kind of additional responsibility. And when you have this object, you can attach this additional responsibility dynamically to this object. Or you could attach this additional responsibility to this object. But moving on further, decorators provide a flexible alternative to subclassing for extending functionality. So it's not just that you can take the concrete decorator and endow the concrete component with the power of the concrete decorator. It's very, very flexible because as we were saying before when we were talking about this, you could take the concrete decorator 1 and also the concrete decorator 2 and endow the concrete component with both of them. Or you could take the concrete decorator 1 and create 10 instances of it and wrap them in each other and then the bottom wrap it around the concrete component. So you have a concrete component that's endowed with 10 concrete decorator 1s. And in some scenarios, in some applications that might make sense, in some applications that might make no sense. For example, think of the cost method that we had before. If the cost method were multiplying and if the cost of concrete decorator 1 was 1, then it wouldn't matter if you were wrapping multiple 1, because if the decorators that you're wrapping all multiply by 1, then you would get the original price anyway, because you'd say, okay, I have this base cost and then I multiply with 1 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 and then I multiply with 1. So in that scenario it makes no sense. But the decorator pattern is completely agnostic to your scenario. So syntactically, programmatically, you can do that. You can wrap it just as many times as you want. But in some scenarios it's just not meaningful. But essentially I think this is how they're thinking when they're saying that it's a flexible alternative, because it's actually very, very flexible because you can compose them in any way you like. Let's now super quickly look at a code example. Let's stick with the coffee example. So we'll start with the abstract beverage class. So we'll say abstract class beverage open, and I'll skip the description methods just to keep things short. So remember that. I'll only do the cost methods. So because of that, we only have public abstract cost, the cost method. Remember that because it's an abstract class and we don't want to give cost and implementation here in the beverage class because we don't have a baseline cost for beverages. We need to know which type of beverage it is before we can give it a baseline cost. We declare it as abstract because then we're saying that whoever subclass is beverage has to give an implementation of cost. That's that for the abstract class. And then let's do the add-ons. In other words, the decorators. So then we have abstract class add-on decorator. I'm running out of space here, but continuing on the same line, is of type beverage. Because remember again, the decorator is a component, so it is a beverage. And the implementation of that is just that the abstract class is stating that if you are an add-on decorator, then you have to give an implementation for cost. Because again, there is no baseline decorator. This is only so that we can have the same type of all the decorators. So that's why we're saying that they need a public abstract method called cost. And again, no implementation. So in this particular scenario, just to be a bit more complete, of course, we don't actually need the add-on decorator. We could just say that all of the decorators behave as beverages and have beverages. Moving on to the concrete implementations. So a concrete beverage, let's only look at espresso. Remember, we had decaf and we had espresso, but let's now only look at espresso. So then we have a class called espresso, which is of type beverage and has an implementation for the method cost, right? Because it's a beverage, it needs to implement the method cost. So it has a public, of course, I forgot the type here. I forgot the data type here. So let's actually quickly add that. Public abstract int cost and public abstract int cost. Probably it makes sense to use a double or something like that, but let's just keep it simple. Let's stick to ints. So the espresso needs to have an implementation for public int cost. It needs to have an implementation for the cost method. And what do we return? Well, I think before we said that the espresso has a price of 1. So because it's the baseline implementation, because it's the base case, because it's the innermost thing, because it's the actual beverage, then we actually just return whatever the price of that thing is. So let's say we return 1. But what happens at the decorator end? So in the decorator end, let's do the caramel add-on. So then we have a class called caramel, and that is of type add-on decorator, running out of space. So the class caramel, which remember is a decorator, so in a real world scenario, remember I said before I would probably call this caramel decorator, just to be explicit, so that when people see the word caramel, they know that it's not just a standalone class, it's actually a decorator that needs to decorate something. So the caramel decorator is a add-on decorator, and the add-on decorator is a beverage. So by proxy, the caramel decorator is a beverage. So back to that idea. The decorator is and has a component. And now we've only described that it is a decorator, but because the decorator is a beverage, it by proxy is a component. But then to the has part, we say that a decorator has a component as well as is a component. So how do we describe the has a component? So we describe that by saying that it has of type beverage, let's call it beverage, and before instantiation we can't know what that is. So for the constructor, public caramel, so in the constructor, public caramel, we take an argument which is of type beverage, let me just call it B, so that we can differentiate between the beverage that's passed in through the constructor and the beverage that exists as an instance variable. So then in the body of the constructor of the caramel decorator, we do what? We say this dot beverage, in other words, this instance variable beverage, we say this dot beverage and assign that the value B, close the constructor. So what happens here? We assign to the instance variable beverage. Here we say this dot beverage. In other words, we assign to the instance variable beverage, we assign it the value B. And B is what was passed in here through the constructor. So we have a beverage here in the caramel decorator, and after construction, after we've instantiated the caramel class, we will have set the value of that beverage to whatever was passed in through the constructor. So again, the caramel decorator class has a beverage that's set through the constructor, but also is a beverage, because here by proxy it is, because it is a decorator and the decorator is a beverage. And that was the constructor, but then now we have to also implement the cost method. So then we say public int cost. And what's the implementation of that? Remember, we drew that before when we said that the difference between the cost method of a decorator and a component is that the component is standalone. So the component can actually return its own cost, whereas the decorator cannot exist in isolation. It has to decorate something. It has to decorate either another decorator or it has to decorate a component. So that means that when we ask a decorator for its cost, it can't just stand alone report its cost. It has to report its own cost in relation to the thing that it's decorating. So that means, as we drew before, that we can't just say return some kind of cost here. Instead, what we do is that we say return this dot beverage, this instance variable beverage, this dot beverage dot cost, in other words, calculate the cost of that, plus the cost that's for this caramel decorator. And I'm not sure if I remember correctly, but let's just say that that cost is 2, for example. Could be something else, right? I can't remember if that's the same as we had in the example before. So in other words, we take whatever the cost is of the beverage that were passed in through the constructor, and we add to that 2. So when you have some kind of beverage, and then you wrap that with the caramel decorator, then when you ask the caramel decorator for cost, the caramel decorator will ask the beverage that it's wrapping, let's say that that's the espresso beverage, it'll ask that for its cost. So we have the call to cost here and we have the same call to cost here, but inwards, and then this espresso beverage will return 1. So 1 will go up here, but then the caramel decorator will take that cost and add to that another 2. So here we get 1, and then we'll get another 2 here. But of course it's 2 plus the 1 that we already have, so we get 3 out here. And that's essentially it. The methods that we have in all of these places are completely dependent upon your scenario. And the number of decorators and the number of components that you have are completely dependent upon your scenario. So when we looked at the generalized UML diagram, we said decorator 1 and decorator 2, and we said concrete component. But you can have any number of concrete components, and you could have any number of concrete decorators. So that's sort of on the class level. And on the method level, you could have any number of methods. So here we happen to talk about only cost, and in the earlier versions of this example we also talked about descriptions, so the fact that all of these had descriptions. But you could have any number of methods, and in the generalized we said method A and method B. And I also want to add that when I said that the decorator cannot calculate cost in and of itself, I mean that's accurate, but it's also dependent on this scenario. So in this particular scenario that's true. So when I say that the cost method here cannot be computed without also looking at the cost of the component that we have a reference to, in other words, without looking at the cost of the beverage that we have a reference to. That's dependent on the scenario. Generally, the cost method could, of course, calculate something without looking at what it decorates. So now we're leaving the whole context of a coffee house. So just generally, if you have something that's decorated by something that's decorated by something that's decorated by something, and then perhaps this decorator is something like a reset decorator. So you make a method call to the outermost decorator for something, and then that call is passed in and passed in and passed in. And perhaps this decorator completely ignores what's down here. It completely ignores what this decorator reports, and thus by proxy completely ignores what the component, what the inner component actually reports. So decorators can be used for tons of different things. And if you want to think of it in terms of math, you could think of it as this thing multiplying by 0, for example. And if you would multiply by 0, then it doesn't even need to look at what's inside. It doesn't even need to further the chain of making calls downwards towards the component, because it's not going to matter what's in here, because it's still going to take, let's say that what's in here we call x. We don't need to compute x because we're still going to multiply x by 0 when we get to this point. So then we could just say return 0. So again, the implementation of the methods that you have are completely dependent on what you're actually trying to model. The point here is that you can construct this kind of component that you decorate, that you decorate, that you decorate, that you decorate, and then in some sense recursively, quotation marks, construct the value that you want. So you make a call to the thing in the outermost layer, then makes a call to the thing it's decorating, that makes a call to the thing it's decorating, that makes a call to the thing it's decorating, etc. And then the value propagates up all the way back out, and then you have your value. But how that processing of the value or construction of the value happens, again, is completely dependent on your scenario, because it depends on what you're modeling and it depends on what kind of value you're actually looking for. So that's the decorator pattern. Before we wrap up, I said before that I wanted to mention why I don't think that this particular example is actually suitable for the decorator pattern. So in my mind, what we're doing here is unnecessarily complicated for the problem that we're facing. A more suitable way of approaching this problem, I find, would be to have a beverage class, and in the beverage class, for example, via the constructor, you can pass it a bunch of condiments, or as we call them, add-ons, or extras, or flavors. And these are all of the same type. So you have flavors, and then you have concrete flavors sharing the flavor interface, or the flavor abstract class, or whichever way you want to design that. But the point is that you take these flavors, and then you pass them into the beverage. When you construct the beverage, in the constructor, you pass a list, array list, whatever, a collection of add-ons, a collection of extras, a collection of condiments to the beverage. And then when you ask for the cost, you simply aggregate, you simply iterate over the collection of extras and produce a value. When we talk about iterator pattern, for example, you'll see why that's actually a very useful strategy, because you're separating two different concerns. You're separating how to iterate over the collection, how to aggregate a value based on the collection, and the actual values of each of the items of the collection. So the reason I'm stressing this is that when we're using this for decorator pattern, we're actually mixing these two concerns. We're putting the plus here in each of the decorators. And what I'm arguing here is that that's unsuitable because of the thing that we're building. It's unlikely that we'll want to change the plus to something else. It's unlikely unlikely that suddenly if you introduce, I don't know, you put chocolate in your coffee, you want to double the price from before. That's unlikely. Of course, you could argue that multiplying could become relevant if you would look at things such as different sizes of cups. Then it could actually be that the price is the same but double if you have a larger cup. But again, I think this is total over-engineering. We would do much better with just a list and then iterating over each of the values in that list by asking all of the beverages in that list, what's your cost, what's your cost, what's your cost, what's your cost, and then add that up to a single value. So in other words, then the beverages wouldn't have to both produce their own value and add that value to whatever was before. I'm arguing we're mixing two concerns here that shouldn't be mixed. And probably, if I try to generalize here, probably the problem lies in that the decorators are too much alike. So we're looking at a scenario where it's unlikely for any decorator to be significantly different from another decorator. If the implementation of the cost method is significantly different between decorators, then I think you're looking at a scenario where it's actually potentially very useful to use decorator pattern. But if what varies between these different decorators is a single property or multiple properties, essentially, if what varies is a property, then you're probably forcing in a pattern where it's not suitable. So the Head First book actually has an example which is actually much more appropriate, which is from the Java API. So if you're in Java, you perhaps recognize the concept of an input stream. So you have an input stream which could, for example, be a file input stream. So if you're streaming from a file, you're reading the contents of a file from disk, and then you can decorate that file input stream with, for example, a buffered input stream, with, for example, a line number input stream, etc., etc. I mean, I'm not familiar with this API, but just by reading these names, I'm trying to guess what they're doing. So the buffered input stream would probably help you buffer, in other words, read in chunks. So you take a buffered input stream and then you wrap that around an input stream. And then perhaps you would take a line number input stream, which I guess helps you to get the line numbers as you're reading. So for example, you construct a line number input stream and wrap that around a buffered input stream that's wrapped around a file input stream. So to me, that sounds a lot more sensible. And I think for two reasons. One, because we're talking about streams. So the decorator has a name that resembles the thing we're decorating. The decorator is named stream, and the thing we're decorating is also named stream. Whereas if you think about what we've been doing, we've been saying that condiments, add-ons, are beverages. But obviously they're not. And that's one of the reasons I think this is actually kind of a strange example. Because decorator pattern is probably more suitable when your decorators actually very much are what they're decorating. But again, the second point is probably a lot more important, and that was that the differences between these different decorators is so insignificant that decorator pattern is simply not probably sensible. If the only variation is the actual cost, and when we had more stuff, the name of the decorator, in other words, the name of the add-on or the name of the condiment, as in like, is it whipped cream, then those are sort of on the property level and not on the behavior level. I think decorator pattern is probably more suitable when we're looking for behavioral variation. We're not looking for variations in that here we have a 2 and in the other one we have a 3. That's not a behavioral variation. We're actually looking for variation in this plus. That's when decorator pattern is more useful. When in some of the decorators you want to use plus and in some of the decorators you want to use minus. For example, probably math isn't suitable either because order matters. But just again, think of the input stream example. When behavior is significantly different between the different decorators, the same method and the different decorators. So a very small example of when I've actually used something that looks a bit like decorator pattern in actual production source code is when I'm trying to deprecate something, but I don't want to deprecate it in all of the places at once. So assume I have this object, I have this class, and it's used in a bunch of different places, and I want to stop using this particular class, but for some reason I don't dare to change it at all places at once. So I'll create a wrapper, I'll create a decorator that decorates this thing and somehow intercepts the operation here. So for some of the methods that I may want to deprecate, instead of making the call to the thing here, I just ignore making that call and let the decorator return a value. Or I, for example, do make the call, but then somehow augment the value. So that means that I can use the decorated version in some places where I'm ready to change it, and I can use a non-decorated version in other places. So that just makes deprecation easier. So last thing before we close this thing about decorator pattern, and I forgot to actually show how we would use this. So how would we go about creating a caramel decorated espresso? What we would do is that we would say new caramel, and in the constructor we pass a new espresso. And then we can save this into some variables, let's say beverage b equals, pardon the double lines. And then if we call b.cost, where we end up first is that because it's on the outer level, because it's a caramel class, because it's a caramel decorated, we end up here in the cost method. So when we call cost here, we say, okay, return this.beverage.cost. In other words, we can't do +2 first. We first need to look at the beverage that I have as a decorator here, the beverage that I'm decorating. So we go into that beverage, which happens to be an espresso, which happens to be this class, and we call the cost method here, right? The beverage.cost. We call this cost method, and then that cost method happens to return 1. So here we'll get 1, and then we add 2 to that. So we get, in essence, return 1 plus 2, because we add 2 to it. And then we're back here, and then this line then essentially equates to 3. And of course, if we had multiple decorators, here when we said new caramel and we pass in new espresso, we could just keep on passing other decorators or wrapping with other decorators. So we would say new decorator 1, and then through that constructor pass new decorator 2, and through that one's constructor pass new decorator 3, and through that one's constructor pass new decorator 4, etc., 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 all the way down into the innermost constructor where we'll pass a component, and then we hit the base case. Whew. So that's the decorator pattern. I hope that makes sense. If not, let me know and then we'll try again. The link to the book is in the description. Tons of more good stuff in there. This is a playlist. We're walking through all of the patterns in this book. So in order to not miss the next pattern, if you're not already subscribed, be sure to subscribe. Thanks for watching. I'll see you in the next one.